All right, so today the request was made in reference to that of the gas laws. So, what gas laws did we learn? There should be 4 of them. Okay? So, the volume times the pressure equals the pressure times the volume. Oops, that's not right. Okay, Charles was another one. Okay. There's 2. 2 down, 2 to go. Okay. The ideal gas law. And then we're leaving a little bit of a gap in there for a significant reason. We'll get back to that in just a moment. But yet there is one gas law that we still need to make reference to. What happens if you put these 2 together? Just like a piece of farm machinery, when you take this working motion along with rotating, I don't know how accurate that is, but you take 2 simple machines and put them together, what's that called on the farm? Close, a combine. Okay? The combined gas law, which then means you're combining these 2 together. You wouldn't have volume and volume. There we go. Now, there are certain requirements for these, so it's not so much for these 2, but especially this one here. So what do we know about converting these? Pressure needs to be in what? No. Okay. The volume should be in liters.
And as a given value.
Moles.
Okay, so that's your given value. Okay.
Temperature in Kelvin.
Okay. So I think for our purposes, I believe this is where we want to spend the majority of our time on.
Isn't M moles?
Well, sure, it may be given, or you could be given every variable and then you're solving for moles, and then from your number of moles you could determine how many grams of that gas are present. Okay? So then one of the aspects that when we look at this, some people chose, I am an ideal gas law individual. Other people may have said, well, I would rather do this. Well, duh. That's not how you spell duh, though, is it?
No, I don't think so. I think it's DUH.
Okay, yeah. Okay. And then one of the things that for what I believe, I think a lot of you students would believe is true, that this also makes things just a little bit easier, and you may choose to solve for that just using dimensional analysis. Yes, the ideal gas law always works, and sometimes you have to use the ideal gas law, but there is, again, some dimensional analysis, but if it's measured at STP, you can just use straight dimensional analysis. All right. So, even when we're dealing with this gas law, you have to have a balanced chemical equation, reaction, whichever. Okay, So we can just make one up on the fly, and what that would possibly mean is, all right. What metal do you want to harvest from the from not the Earth's core? That's not what I mean.
Mercury.
Okay, well, we can do nickel. All right. So the reason we say that is because of when you harvest these metals out of the ground, you don't take pure nickel out of the ground. You don't take pure copper out of the ground or pure aluminum. It's mixed with oxygen, which means it is a what?
Oxidized.
Well, sort of. It means it's an ore, not O-R, but O-R-E. Okay? So we chose nickel, correct?
Yep.
All right. So if that is the case, harvesting, oops. Quite a large sample. Well, I guess I don't know how much large would be. 1,300.
27.
Okay, 1,327 grams of I would be led to believe that this nickel ore would be this here. Nickel, I'm running out of space. I can put a little gap in here. Nickel 3 oxide, okay? So we're harvesting this 1,327 grams of nickel 3 oxide, okay? How many we'll do this. So how many milliliters of this oxygen are released when smelting it, okay? So what that means is you're taking this, yes, you're essentially burning so you can separate the oxygen from the nickel. So however, whatever size that is, depending upon how dense nickel is, maybe it's the size of this mug here. Now, we need to be a little more specific because of all these variables here. You can make this as simple. You want it at STP.
Yeah,
And that's fine. Okay. Okay. And it's released when smelting at STP. Okay. And we can go through and do this both ways because some people, I'm a dimensional analysis person. No, I'm a ideal gas law person. So which way would you like to see first, the dimensional analysis or the ideal gas law?
ideal gas law.
Okay? So then, if we're doing the ideal gas law, what do we know?
Pressure in your tank.
Okay?
And your R.
You got time.
So we know pressure is 1 atmosphere. Okay? We know the volume is what we're looking for because a classic mistake, because if you're in a hurry, you're going to look at this and say, well, we've got that already. Okay? That's not how that or where that goes. Okay? Because the question's asking how many milliliters. Okay? So that means you have to be looking for the volume. So then this value we don't know, of course 0.0821, and then you said 273 degrees Kelvin. Now, one of the aspects that you can help yourself out, there's a repeating pattern with this every time. What did we have written here that we erased?
23.
Well, is it a coincidence? What happens, do you suppose, when you multiply those two together?
You get 22.4.
There's where your 22.4 is possibly utilized. Okay. So then, it looks to me like what we could say is 22.4, because we multiplied those two, okay? 22.4n equals whatever is on this side, okay? Well, we'll switch the equation around, okay? 22.4n equals what is on,
1B.
okay? Do we have a problem there?
Yeah, 2 variables.
Yes, we do. We've got two variables there. Now, I know you learned in algebra you can do two unknowns where, isn't it something like you solve 2x plus 3y equals 9, and then maybe x minus 5y equals 10. For some reason that seems to look familiar. You move this to the other side and you put x in for whatever you solve for. Or is that bringing back bad memories?
Yeah.
Oh, yeah.
Oh, okay. So if this isn't getting us anywhere, what can we do with this here? Because we haven't used this number yet. Okay? So that must mean, and convert it, that's right, 1,327 grams. Nickel is Ni, okay? Oxide is just what?
Oh,
Okay? With the way that is written, does that add up to 0 right now? If it was nickel 2 oxide, yes.
You got nickel 3
We've got nickel 3.
though.
So how do we have to change this?
203.
Okay? Now we have nickel 3 oxide. But is there a problem with just converting that to moles? Yes, there is. Because what are we really looking for? We just want that. This is what we have right now. So that presents a problem. I'm sorry, write out what? Not only that, you have to go through a mole-to-mole ratio. So that must mean that this nickel 3 oxide, Ni2O3, when that is smelting, what are you separating?
The oxygen from the nitrogen.
Okay, so that leaves us our nickel plus,
O2.
okay, also don't leave that behind because oxygen's diatomic, okay? So these oxygens are odd, those are even. Get this up to an even number. In order to do that, we need to do what?
243.
Okay, 2 times 2 then gives you 4. And 2 times 3 gives you 6. So how do we get 6 oxygens? Okay, now we can proceed with this. Okay? Go ahead and get that box off of there. Okay. Then, how many steps is this going to be? 4? 3? 2?
That's a 2.
Okay, we'll see if 2 does it. Do I hear 4? Come on, get in on this auction. I heard 2, I heard 3. Who wants to vote or bid 4?
Open 4.
Okay, 4. We have 4. How about 5? 5, 5, 5. Anybody? Up. 5, 5, 5. Oh, 6, 6, 6, 6, 7, 10. Okay, 35. Anyone want to outbid? 35.
Sold. Take it.
Going once. Oh, I'm missing a sidekick, aren't they supposed to go, hip, hip, hip?
I got
Yeah.
the highest bidder.
Okay. So, all right. So went for 3 times, it's sold. Okay, how do we get grams to cancel out in this step?
You gotta put the total, 165.38.
153,
165.38.
165. Now, you didn't just make that number up, okay? Because we got to take 58 maybe for nickel. Take that times 2, so that gives you a little bit over 100. And then 16 times 3 gives you 48. You add those two together, that's where the 165 is coming from. Now you're in moles of nickel 3 oxide. Okay? So we can abbreviate that because we've established that here, but we don't want moles of nickel 3 oxide. We want moles of what? Of oxygen. Okay? So for every mole of nickel oxide, we get a mole of oxygen. And even though we're not solving for a mass, it's still good practice to keep that 2 there. Now we have to go back to our equation. What's in front of nickel 3 oxide? From that 2 goes here. What about your oxygen? 3 goes in front of there. We're in moles of oxygen, and that's where we want to be because all of these have canceled. And then whatever we get here now can go up into that equation. Okay, so 1327. Well, first of all, I'm going to take 165.3. Take that times 2 and get 330.60. Okay? And then we're going to take 1327 times 3 and get 3981. So once we divide all of that out,
12.04.
okay, which gives us 12.04, okay? And then that, of course, is moles of oxygen, which now we can put this up here. If we take 12.04 times 22.4, that would give us 269.70.
Times that by 1,000.
269.70, and then that's in liters. So then we need volume equals 269,700 milliliters. Okay. Kind of messy, yes, no. A lot of work here. But there's something else that we could do, and that is as follows. Okay, I'm going to go ahead and get rid of this. But maybe we just wanted to use straight dimensional analysis for this, which we still can do, because even if you're an ideal gas law person, we can see that there's just a little bit of dimensional analysis with that anyway. But if we do this, 1327 grams of Ni2O3. Now we're going to our 4-step problem, maybe even 5 if you wanted to do that. So we still have to divide by 165.30 grams of NO gives you a mole of NO. Okay, then just like what we did here, for every 2 moles of nickel oxide, you get 3 moles of oxygen. Okay, then this is where our final conversion takes place. because for every 1 mole of a gas, how many liters do you have of that gas?
269.
Nope. Nope.
22.
22.4. Okay, so if we put 22.4 here, now you could combine two steps into one and say 22,400 because we're looking for milliliters, but we'll just leave this as 22.4 liters for every mole of O2. Okay, those have canceled. Everything's gone except for our liters of O2. So that must mean that if we, I wished I wouldn't have erased that. I think that was what, 330? 165.3 times 2, 330.6. Okay.
Give us any questions about Charles and
I would say at this time, no. That's why we're spending time on this one.
For, if you do though, is the volume, it'll be measured in liters, right?
Yes, it's just here it's asking for milliliters.
Yeah, but for those ones like Charles and,
If we do those, yes, the volume would be measured in
so
liters.
the only gas law is that, this one. is the
Yes,
volume.
this is one that we for sure want you to know. Okay, so 330.6, we got to remember that number. Times 3 times 22.4. And if that gives us 89,174.4. But if we divide that by 330.6, that gives us 269.73.
yeah,
Okay? But again, that's measured in what?
liters,
And we want it in liters, so which means you got to take 269.73 times 1,000, which doesn't quite give you this exactly, but it's two different ways to get or arrive at the same answer. So then the one written here, I should just keep that in blue, I guess. That way we can say it's color coded, that our volume now equals 269,735.
over under 20 questions on the semester.
Over. I don't know for sure. Because if there was over, some of those may be just stating, okay, draw this amino acid, draw that amino acid. We're familiar with that because that's the most recent content. Let's see here.
Walk in the park.
Will most of the questions be about recent content?
No.
No.
Okay. So there is your ideal gas law, whichever way you choose to do that. You get very much the same answer.
Can we do a limiting reactant percent?
Limiting reactant, N% yield. Before we move on any further, front row, ideal gas law. We're good? Okay, front row. We'll be here a while. Oh, well, maybe. Okay, second row. The first row decided to chime in. They're all right. Third row. Which kind of reminds me, what is it? Maybe some. The different volleyball introductions. Some people clap their hands. I've seen. You have seen this before too. So, how do we do it next year?
Smile and wave.
Whatever way Caitlin wants to do it.
Oh, maybe so. I think maybe you could say it's a 3-headed horse, 4-headed horse. I don't know. All right. So moving forward then. Limiting reactant and percent yield. Okay. Okay, we just stated that we really don't know how well we would do with this limiting reactant percent yield problem. We just decided to make this up on our own. So this can be confusing if we don't look at this beforehand, and that's why we're doing this now. So hydrogen, okay, reacts with chlorine. So there's our hydrogen. Here's our chlorine, and we're making this hydrochloric acid, which would be what? HCl. This could potentially be mistake one. Okay, hydrogen's diatomic, so is chlorine. Okay, so this might throw our results off because we have two diatomic molecules, and we'll see. Then what happens on this side then? Right, because remember, subscripts don't go to that side. They may. The subscript may go over there, but could be wrong. The only ones that do that is something like that.
There won't be any of them, is there?
Well, there could be. Polyatomic ions, sure.
Oh, yeah.
Yeah, that's what I mean. Those subscripts have to go to the right side. Okay, because it's part of the formula. Okay, so then the next question you have to ask yourself, okay, are you battleship students or people, or just straight dimensional analysis for this as well?
Straight dimensional analysis.
We can do both. Which one would you like to see first? Okay, well, they do both involve dimensional analysis. It's how it gets interpreted that's different. Should I just pick? Okay, we'll do the battleship first, which means we've got 10 grams of this. We've got 30 grams of that. The reason is this is only how much we have as a mass. We need to convert these to moles first. So then 10 grams of H2. Okay, that gives us 2.02 grams of hydrogen. Gives you a mole of hydrogen. Okay, so then that's pretty close to 5, maybe just a little under. In other words, 10 divided by 2.02, 4.95 moles of H2. And again, that is how much that we have of this substance. We have $4.95 to spend. Then we need to look at our chlorine then, which means 30 grams of Cl2. Okay, so do we see the reason to keep writing down these subscripts? Because when you do that, the chances, you're lowering the chances of making a mistake.
70 point something, I'm guessing.
Okay, so 30 divided by 70.90. 0.42. So this could possibly be a next mistake that we might do besides balancing the equation. We have 42 cents worth of chlorine. Now's where we play this, what we call battleship. We shoot at this to see how much is required. This we shoot back to see how much is required. So in order to do that, okay, we're going to for every mole of H2, there's a mole of Cl2. And it just so happens that it is a 1-to-1 ratio. So this really doesn't matter. We need 4.95 moles of hydrogen. No, not hydrogen. Chlorine. Okay. Then we gotta have to do the same thing down here. For every mole of Cl2, we need a mole of H2. Again, 1-to-1 ratio. And 0.42 moles of C. Oh, darn it, I did it again. Almost did it again. H2. And then one of the things that we would do to help us out here is we would write REQ. REQ. Okay? So, we need 42 cents worth of hydrogen.
That's right.
We had $4 of it.
Yep.
Okay? We need almost $5 worth of chlorine. And how much did we have? Not enough, 42 cents worth. So again, you just can't look at these and say, oh, since we have less hydrogen, that must be our limiting reactant. That would be a bad way of looking at it. Okay? So that must mean that since we need 4.95 moles of chlorine and we only have 0.42, that means we are really, really short of this. This is our limiting reactant, the chlorine. Okay? So now that we've established that, we really don't have to reinvent the wheel here. Which one of these can we erase? The top or the bottom? Because remember, we've established our limiting reactant. It's the chlorine. So, yes, sir. So we want to go back to what we started with, okay? Because that's why this is important. Now that we've labeled our limiting reactant, we can get rid of all of this. Okay? And then we can get rid of all of this. Because again, we have established our limiting reactant, and we need to convert that grams of chlorine to grams of what now? Hydrochloric acid. Okay? Now, for every mole of Cl2, we can jump to this side of the equation now because of this mole ratio. But we're not quite done in that step. Yes, because of this coefficient of 2, we need to have a 2 there. Okay? Now we're on the home stretch. For every mole of HCl, we get grams of HCl, which is somewhere around 36.45, I think. Okay. So now it looks like 30 times 2, that gives us 60 times 36.45. Okay. And then divide that by 70.90. 30.84. Okay. Okay. Now, on pencil and paper, which yield are we calculating? And I know it was a long time ago, because remember we have this formula, our percent yield equals our actual yield over our theoretical yield. But on pencil and paper, it can't be this one because that's what we're asking for. So on pencil and paper, which one of these yields are we calculating? Right. Theoretically, we should be coming up with 30.84%. Yield equals 30.84. What we actually produced was 24. So then actually our percent yield is going to be quite high. Okay. That was one way to solve for your limiting reactant. We said there's two different ways you can do that. I'm just presuming that we can wrap this up here. I hope. I mean, we worked hard enough to figure all this out. I think we can figure out that percentage. Okay. But then a second way of determining your limiting reactant could be as follows. We started with our chlorine. Well, let's start with our hydrogen ones. 10 grams of hydrogen. Okay, we could do 2.02 grams of hydrogen. Gives us a mole of hydrogen. Then for every mole of hydrogen, how many moles of HCl do we get? That's where that 2 comes from. Then for every mole of HCl, we get 36.45 grams of HCl. And we're in grams of HCl, which is where we want to be. So then, upon doing this, if we take 20, 10 times 2 is 20, 20 times 36
3,600?
gives you 729, and then we divide that by 2.02. That gives us 360.89. Now, you might be asking, well, why was that important? This also determines what your limiting reactant is. Because if you start with 10 grams of hydrogen, you produce 360 grams of this hydrogen chloride. But if we only start with 30 grams of chlorine, we're only making that much HCl. An alternate way of determining your limiting reactant. First one's the battleship way we talked about. You convert this to moles, then you convert that to each other.
What do you recommend?
I don't know. It kind of goes back to your ideal gas law or dimensional analysis. You need to decide what is best for you. Because, okay, if you're having a contest around the green, okay, if you are, some might decide to putt from really short grass, some may take a short iron and use that. You need to decide, what person are you? Some are going to say, no, I'm going to putt. No, I'm going to, I think they call it what, the bump and run, I think. Okay, that might be what you choose too. You have to decide that, not myself. Okay, that was quite a bit of content. So that's all I have. We'll catch up to you next time. Bell's about to ring anyway. All right.